Chat. Okay, so we'll start right away. Sorry for the small delay. It was a small technical problem. So let's continue. Today we're going to start with an example, and the example will be how to calculate the electric field and the relevant quantities for a construct which is shown on the board. So let's assume this is the current, which is shown over there, I0 cosine omega t. The AZ, we don't really need to include that one. We don't really need to assign what the direction is going to be. But we just want to kind of remind you of that picture, which you see it over there, which means that how we can relate the current to the other vector fields and initially to the vector potential A. And then we come back to this aspect here. And in terms of trying to determine the direction of the electric field, what we are going to implement here is that we are going to use the relation where the induced electric field dot dl, this is equal to the minus the rate of change of the flux as a function of time. This is okay, theoretically that is correct. Now, if we do it this way, then these arguments which are over there on that side of the board, they can make sense, okay? Because as we said, we can have the current I, we can determine the direction of the vector potential A. From the vector potential A, we get B. From B, we get the E. And these directions we can kind of conclude they are this way because the current of A is equal to B, and the current of B it is proportional to E. Okay. And now we just come here to this part, and what remains for us is that we need to determine the flux. But before we calculate the flux, we should know what is the magnetic field. Magnetic field is equal to mu0 I divided by 2 pi r. And this one, we find this. Now, we have solved several examples regarding this, and we used to do these relationships. BdL, this was equal to mu0 times I. Okay. And now, when we integrate B across dl, the path that we are going to select is going to look like this. So dl, it is equal to 2 pi r. So if we divide by 2 pi r both sides of the equations, finally we get this. This is an expression which we could also include this one in the formula sheet or in the cheat sheet. So this is how magnetic field is changing. It's changing as 1 over r. If we increase the r, we get smaller b. Now, in terms of trying to determine the electric field, let's think for a moment the following. So let's construct a path that looks like this, and we define this path from radius r to an outer radius a. Okay? And we want to see what is the, and let's also assume that this is some length scale L, okay? And as the first stage, since we're looking for the rate of change of the B as a function of time, we found the B. Next, we need to find the flux phi, and this is B dot dA. And now this B dot dA, it is going to, whenever we try to calculate this integral, we have to determine a series of points where the magnetic field intensity is equivalent. Now, if the magnetic field depends only on R, one could argue that here, all the points along this infinitesimally small segment dr, the magnetic field is constant. Okay, so this is the logic that we're going to assume that this is equal to B times. So let's use the common language is at the distance r, we select an infinitesimally small segment dr. So this is going to be L dr. And then But the integral, we do this one from R to A, okay? And because it is going to be a little tricky, when things can get a little difficult here, we're going to just integrate that zero to the guy. So to put the integral that zero, we actually need to be right. If we substitute R equal to 0, this gets infinity, we get in trouble. So let's assume for a moment that this is from R to A. If we do this, this is mu 0 I divided by 2 pi R times the dr from R to A. And then this is going to be equal to mu 0 I divided by 2 pi Q heaven L dr over R, etc. We know what this integral is going to be. This is ln of ln R. So this is mu 0 I times L divided by 2 pi ln of A over R. Okay, that's good. We should never forget that the current here, this is a function of time. Okay, so that means that this flux here, we can write it like this. This flux, it is an expression of time. So it's not constant. Time dependency, it's hidden here. Then the next step is that we need to determine the d flux over dt. And d flux over dt, it's going to be equal to, we can pick out all the constants out. So this is going to be mu 0, not I, sorry, I. It has a time dependence in it, mu 0 L divided by 2 pi ln A over R. So again, let's say the rate of change of flux, it has a radius dependency, which is hidden in here. Then we take the derivative of the current, then here we multiply I0, we get a minus sign times minus 1, because the derivative of cosine is minus sign, minus 1, times omega, and the rest is sine omega t, sine omega t. So this is d flux over dt. Now, if this is d flux over dt, then we can, let's see for a moment, so this is, yes. This is the electric field, E dot L. This is, and we have to include, so this is the rate of change of flux, but since we have a minus sign here, allow us to put a minus sign right here, and let's change this one minus 1 into a plus 1. So this is the rate of change of flux, and meanwhile, we assume that the integral of EdL, it is going to be equal to EL, okay, the electric field times the L. The argument to do this is that since this is the dot product between E and EL, and E is going to be along this set, we are going to get a non-zero term only when you do the dot product here, right? Because E is still going to be equal, is going to be with an angle of 90 degrees with respect to this one. So this is what we get for the E. At this stage, we see that we have an L here and an L here. So where did this L come from? It came from the infinitesimal surface area element, which was LdR. So this is the surface area of this term. So it looks like the electric field, it is going to be mu 0 divided by 2 pi, we have I0 omega, then sine omega t, and let's try to clear this one, this whole expression. The E, it is going to be equal to mu 0, I0 omega, I0 omega, divided by 2 pi, times ln A over R, the natural logarithm of A over R, times sine omega t. And that's also here in AZ. Okay. Good. So this is what we obtain for the electric field, which is induced. Okay. Now that we have this induced, now that we have this induced electric field, we can we can find other relevant quantities, which could be the induced current and the displacement current. If you remember, we defined so if you remember from the Maxwell's equation, we said that we had 4 different terms. But the contribution of Maxwell, it was that whenever we write down the curl of B, the old expression, it was mu0J. But what Maxwell did, and for this contribution, he even all the 4 equations, they were given his name, was that he added this new term here, mu0, the rate of change of D, with respect to time. D itself, it's equal to epsilon 0E, and then the derivative of the displacement vector as a function of time is going to be here epsilon 0E, and here with respect to time, and this is equal, this is a constant, we get it out, so this is epsilon 0 dE over dt. And this whole term, this is going to be equal to the JD. So this is the displacement current, or it's an induced current, which is happening because of the rate of change of the electric field. So at this point, actually, we could erase this one, because this is an almost classical expression. We wrote that one just to prove or to remind that the magnetic field is going to change like this. So then, at this point, we can define almost 2 different current densities. These 2 current densities, one of them can be the conductive current, because this is JD. But we have also the conductive current, which is described as sigma times E. Now, why do we call this one conductive current? This is the current that flows through a wire. If we have a wire where the electrons do travel, we can assume the following. So this is the current IC. There is a conductivity of the wire. There is also some electric field between 2 points if we have a potential difference across a wire. Right? So at this stage, we can assume that or we can write the following. We can say that wait a second, let me see for a moment, just the numerical value of the numbers that we have here. 6.87. This is what we got, mu0 I0 divided by 2 pi sine omega t. Yes, yes, we need to find let's say the displacement current. Okay, yes, then let's take the rate of change of this electric field, and then dE over dt, and when we take the derivative as a function of time, this is the only term which depends on time, and finally we're going to get mu0 I0 omega squared divided by 2 pi ln A over R times cosine omega t. So this is the rate of change as a function of the electric field as a function of time. We can multiply by epsilon 0 both sides, and here we can also put epsilon 0, and this will be really the displacement current JD. So somehow we determine this. Now let's assume for a moment that let's assume that we want to calculate the total current which flows across this problem. Okay, so let's not forget we started from a current that flows upwards, and we can draw this again because this figure maybe got a little too much information. So we have initially some current which is as a function of time, and as a result we're going to get current densities which are there effectively just because of the existence of the magnetic field change as a function of time. So overall, we can say that effectively the whole current which is flowing upwards is equal to the ID, the displacement current, plus the IC. Okay, so the current which is flowing through the circuit plus this. So overall, we have some way more, and this current ID. We can remind ourselves that the unit of JD, JD, current density JD, which I'm asking, what is the unit of the current density? The current density is measured with what? It is ampere per meter square, okay? So that's what it is going to be. And ampere per meter square. So the displacement current, ID, it will be equal to JD times the area, because this is M per meter square times meter square, and this is what we are going to determine. Now, if we do this integral, we can find that the displacement current is going to be equal to, so we have a couple of approximations that we have to follow with, and these will be mu 0 epsilon 0 omega square I a square divided by 4. Now this is the ID. Now an important question is also the fact, not the fact, but it's an issue of comparing how does the ID compare with the original current. Because it could be that for any specific construct, we can have a current I, and new currents are going to be induced, but as new currents are going to be induced, this might generate a lot of heat, and we know that the heat generation is described by the power on the surface, which is equal to VI, or I squared times R. So, but if this current was constant as a function of time, the displacement current would be equal to 0. Okay, we will not have this one. But in case this is changing slowly as a function of time, we will notice that this is going to increase faster. We can also notice that this is proportional to omega squared. Okay, so this means that a higher frequency, this means that we're going to have a much higher current. So what is this frequency? Let's assume, for example, that we have a frequency of 1 kilohertz. If this is 1 kilohertz, then the omega is going to be equal to 2 pi, because omega is equal to 2 pi f, right? Because omega is measured in radian per second, because this omega, it appears as a cosine of something, and the cosine of something should be radian. So, and then this is the radian, this is inverse second, so this is going to be 2 pi times 10 to the power 3. This is this omega. But imagine now for a moment, if the frequency is in the order of 100 megahertz. If the frequency is 100 megahertz, the angular frequency, or the omega, which has units of radian per second, this will be 2 pi times 10 to the power 8, okay, because omega is 10 to the power 6, times 10 to the power 8. Now, if the current density is proportional to omega squared, that means that this is proportional to 10 to the power 16, okay? Proportional to 10 to the power 16 if we are at this frequency, and it is proportional to 10 to the power 6 if we are at 1 kilohertz. So we have 10 orders of magnitude change in the current density. So if we have several orders of magnitude change, that means that this is a huge increase, which could bring up, can bring up these issues of whether we can lose a lot of energy because of the, what's the name? Heat, let's say that like heat. That's why in this kind of systems, we may desire to have a water cooling system so that the system does not break down. Okay, so if we look at all of these terms that we see here, we can also assume that, and by the way, what is this omega 0, so mu 0, epsilon 0? This is the permeability of free space or vacuum times the permittivity of free space or vacuum, such a bravado. This quantity, okay, so I can erase some parts here. Specificator 3 in free space, this is 3 squared times 10 to the power 8 squared. So this is, so whenever we see these two terms, that's what they are. So then at this stage, let's this is mu 0 epsilon 0, so this is 1 over c squared. So this is 1 over 3 squared 10 to the power 8 all squared times 4 times omega squared. Let's assume the frequency is 100 megahertz. If it is 100 megahertz, then this is going to multiply 2 pi squared times 10 to the power 8 squared. Okay, so this is omega squared times a squared. Let's assume that a, it is a coaxial cable which has dimensions of, let's say, 1 millimeter. Because let's assume that we have so the problem that we are solving here, we have not said anything about what this A can be, okay? But let's assume that these are systems which are reasonable wide. So a coaxial cable can be a cable which has an inner wire where the current goes upwards, okay? And this wire, let's assume this is 1 millimeter. Then we can also assume another case where the radius A, it is 1 centimeter. Let's substitute here for A, 1 millimeter. 1 millimeter is 10 to the power minus 3 squared. So the ratio between the displacement current and the conduction current, which is flowing over the circuit right away. Here, we did not put the I, because when we calculate the ratio, these two are going to cancel each other, okay? So the ratio is including only these other terms. And if we have a look, we notice that these two cancel these two together. We have 2 squared times pi squared, sorry, this is 2 squared, divided by 3 squared times 2 squared, that's 4, times 10 to the power minus 6. So this pi squared cancels out the 3, at least to the order, to acceptable order of magnitudes. So it looks like this is the ratio, it's something in the order of 10 to the power minus 6. But if the wire is not 1 millimeter, but let's say it's 1 centimeter, then this ratio is going to be closer to 1, because we're going to see that ID divided, so displacement current, divided by all of these terms, So it looks like all of these terms are cancelled out. So it looks like this is simply a ratio of a squared. But this is it's a ratio of a squared if the frequency is 10 to the power 8, right? If it is 1 kilohertz, this would be different. So these numbers, they cancel out because we are dealing in this ratio. Of course, this ratio is going to be a function both of the radius of the wire and of the frequency. Maybe it's best if we do it like this. Like a reminder, ratio is equal to ID divided by I. So this is a function of the frequency and of the radius. We fix the frequency, we are dealing at 2 pi times 10 to the power 8. And now we are left only with 8 squared. So if the radius is 1 centimeter, then this is going to be equal to 10 to the power minus 4. Okay. So if we increase the radius again and again, it looks like the ratio is going to converge to 1. Okay. Or we can have a frequency which is in the order of 1 gigahertz, and those numbers will operate closer to the risky values. Now, let's look at a different example. And in the next example, let's assume for a moment that let's assume that we have seawater, and in seawater, the permittivity, it's going to be 81 times epsilon 0. Epsilon 0 is the value for vacuum or free space, the permittivity. And let's assume we have a frequency which is something in the order of 400 megahertz. 400 megahertz is going to be, we can write it like this, or this. Now, at this frequency, we have also that the permeability of seawater is equal to mu 0. Sorry, let's do it like this. The permeability of seawater is equal to mu 0, which means that it's the same like vacuum. So this means that it is non-magnetic. A lot of materials, especially insulators, they are non-magnetic. This one, it has mu 0 equal to mu 0, because this is not magnetic, including several components like a piece of wood. And other than this, let's also assume that we have a resistivity rho, which is something like 0.23 ohm times meters. Okay, so this is what we have. Now, if we are dealing with high frequency, so let's assume that this is not some current that is changing as a function of time, but that this is simply a signal, okay? And this signal is an oscillatory signal because it has 4 times 10 to the power 8 hertz, okay? And let's assume, or let's try to find what is the ratio between the conduction current in the seawater to the displacement current. The question is this: find IC over ID. But now, whenever we try to do this, we can let's assume that the C is something like this. It is like a capacitor, and on this capacitor, we are kind of applying an alternating power supply voltage V. In this case, this V would be equivalent to V0 times cosine omega t, which will be then equal to, so this is our assumption, okay? This is something you did not know, but you can take this for granted, okay? Once you are given this assumption, you could immediately conclude to a solution because what remains to be done after this is simply substituting expressions of some relevant quantity. So here we have cosine 2 pi times the frequency 2 pi times 4 times 10 to the power 8 times time. That's good. So we found the potential difference. That's good. Now let's assume if this is the seawater and if this behaves like a capacitor, it is like a huge capacitor in fact, from the sea level down to some point where we may want to communicate. How would we want to communicate? We are going to learn this very soon, actually. But let's also assume that this is a capacitor with a distance d between the two plates. If this is the distance d, then we can immediately try to relate the quantities that we're looking after. And by the way, what is a series of equations that we can use with the information written on the board? We can see that the electric field, which can exist because if this is V1, this is V2, then the electric field between these two plates is equal to V divided by D. Okay? That's one equation. The next equation, which is very important for us, is that the conduction current JC is equal to sigma times the electric field. Okay. Now, we don't know sigma, but we know the resistivity. Resistivity, it is inverse of the conductivity. So, JC, it can be written as E divided by rho. Okay. These two equations are the same because these two quantities are related like this. That's good. What is the next type of equation which is important for us? The next equation is the conductive current density, the displacement current density, JD, which can be written as epsilon times dE over dt. Let's continue. This epsilon is equal to 81 times epsilon 0 times the rate of change of E. So the rate of change of E with respect to time, this is equal to 1 over d, okay, because the rate of change of E with respect to time is equal to d over dt of the voltage divided by the distance between the two plates of the capacitor. 1 over d is constant, we can take it out of the derivative, 1 over d, then we have dv over dt. At this point, the derivative of v with respect to time is going to be the derivative of this expression, which is going to be, so this is the omega. This is going to be minus 1 over d. We have a minus because the derivative of cosine is minus 1 times v0, which is this amplitude, times, let's multiply this one. 2 pi, let's write this one, times 8 pi times 10 to the power 8 times 10 to the power 8, and then who can help me here? Times sine 8 pi times 10 to the power 8 t. Right? Let's see if we are missing anything. So this is the rate of change of the electric field. Now, actually, we can write down all the equations right here. We can multiply with 81 epsilon 0. So let's multiply here with 81 epsilon 0. And then, yes. Yeah, this is it, right? So we wrote the JD. Now that we have the JD, we just need to calculate the ratio. Okay, so we have IC over ID. And the current density, it's always written like what should I say? The current, the magnetic current, is equal to the current density times area. This is similarly, this current density times area. The areas can be cancelled out, and then we need to write down what is the JC. JC, it is 1 over rho times E. And allow me to write this here. So JC is 1 over rho times E. E, it is V divided by D. Okay, this is V divided by D. Okay, and let's write the JC. Let me do it here. JC, it's 1 divided by rho. Here we have D times V. And this V, it has, so the potential itself, it is times cosine omega t. Okay? In fact, let's assume ne përgjigjem raportin midis këtyre dy rrymëve, për një moment thjesht mendojmë se kur do gjejmë vetëm raportin midis mallësive të këtyre rrymëve. Le ta harrojmë për një moment sa është që kemi se njëra do të dalim sinus, tjetër në kosinus. Sinusi me kosinusin nga velosin plus një ndryshojnë, nuk është ndryshojnë shumë magnitudë. Pra, o është shuzon me 0, you don't see the ratio at all, ose shuzon me 1. So it's kind of, the magnitude is not going to be affected by this, that's for sure. So, I don't want to write the cosine, but I'm writing it down in red just to remind you that's what the potential looks like, okay? But if you want to find the ratio between the magnitudes, this is gone. This is I, the JC. JC, conductivity times C, etc., etc. Now let's divide this by the JD, which is this term, for this whole expression here. And let's continue. This is V0, or let's say here. This is V0 times sine omega t. Again, since I care about the magnitude, you might completely disregard the sine omega t, but let's write this in a different color. This is V0 sine omega t times 8 pi times 10 to the power of 8. 8 pi times 10 to the power of 8. And the d comes up here. So then, if this is the ratio, then we can say that this V0, it cancels this V0, this d cancels this d, and this will be equal to, I think I'm missing something, because here we multiply by 81 pi, right? So we have to multiply here with 81 pi, because initially we just calculated the rate of change of electric field with respect to time. But let's not forget this term, okay? So times 81 pi, no, not 81 pi, 81 epsilon 0, sorry. Because seawater has a higher permittivity than vacuum. Okay. So then we should divide here by 81 epsilon 0. Okay, so let's see what we have. Then on the top we have nothing. Then this is a rho. Rho is, it was the resistivity, which was 0.23. 0.23 is almost 0.25. Okay, around 0.25. So this is like almost 1 over 4. So divided by 1 over 4, we get here 4. Okay. So this is this term, then we have sine omega t, it's gone. Then we have here 8 pi times 10 to the power 8 times epsilon 0. Epsilon 0 is 8.85 times 10 to the power minus 12 times 81. Because epsilon 0 is equal to 8.85 times 10 to the power minus 12. Mu 0, it is 4 pi times 10 to the power minus 7. So the product between these two, epsilon 0 times mu 0, is going to be equal to 8.85 times 4 pi times 10 to the power minus 19. Times 10 to the power minus 19. So this is almost 9 times 12. 12 times 9. This is around 90 plus 18, 108. So this is almost 10 to the power 2. Okay. So with the, yes, almost 10 to the power 2. So this means that this is approximately 10 to the power minus 17, right? 10 to the power minus 17. This 10 to the power minus 17, this is, and by the way, 1 over epsilon 0 mu 0, this is equal to 10 to the power plus 17, which is approximately 3 squared times 10 to the power 8 whole squared. And there's the 1 over mu 0 epsilon 0, this is what they are. So, 81. Is there anything left that we're not written? No. Everything looks good. So, only that we should do this calculation, and we're going to get this 4, it cancels out, we get 2. 1 divided by 2 pi times 10 to the power 8 times 10 to the power minus 12, this is 10 to the power minus 4, times 81 times 8.85, okay? Then when you look at all of these terms, can you calculate this one, what the numbers should show to us? Okay. If you like, we can have a short break here. Okay, Angie says no. Okay, perfect. Stop recording. Too many minutes, but I'm going to stop recording. Niestety. 0.22, so it looks like, wait a second. So the conductive current is smaller than the displacement current. Okay. That is strange. It could be because actually ticket break. Probably is about cutting and none. And just cover. Ja, bitte. Questa cade più spazio. Cade mentre c'è stato cade. Cade mentre c'è stato cade, sempre 10 minuti cade. Cade, ti dico che zero piccare. Questo è zero qui, non stick it there. C'è proprio facciamo vedere. Ok, adesso vedete 0.22. Good. Stop